All right, welcome to the third installment of Rotational Kinematics and Dynamics. Today we are on the dynamics piece. So it's time to actually put everything we've learned together in one big ugly thing and learn about how the forces and everything work. So we need to start with a free body diagram, but there are some major changes that you need to be careful of. The first one is that we no longer consider things to be point masses, so where you draw the vectors matter. Specifically, the force of gravity and the normal force are drawn from the center of mass. Friction is always drawn at the point of contact and along the surface. Okay? And tensions on rotating objects are no longer going to necessarily be the same. And that's actually pretty much common sense, because if it worked any other differently, there would be no rotation. So we say that one more time. Tension, when an object is rotating about it, will not have the same value on both sides. And so we have to approach this the same way we approach statics. We write an equation with F equals ma. We write an equation with net torque equals I alpha. But now we're going to actually equal I alpha, not equal 0. And we're going to give ourselves a try to answer it. Now there's one hint. And that big hint here is that my alpha, my angular acceleration, is A over R as long as there is no slipping and sliding, meaning that I am rotating with rotational motion and nothing else. So today's lesson is actually relatively short comparatively. It's just a couple examples, but I do have you try a little bit more at home today to give it a shot. So number one, a wheel of the unicycle starts at rest and moves to the right at 2 meters per second squared, has a mass of 15 kilograms and a radius of 0.35 meters, and acts like a cylindrical hoop. Ignore the mass of the seat. There is enough friction in order to keep the wheel from sliding. Complete the following. So if I'm moving off to the right, okay, hope you first can see that there's my force of friction along the surface in the point of contact. Okay, I have a gravitational force, Fg. Okay, I also have Fn, up and down. In order to be accelerating to the right, I also have to have some acceleration to the right, and I'll call that Fa. So something is pushing this object to the right. Okay, so let's look at our governing equations. Up equals down, since I'm in equilibrium up and down, so Fn equals Fg. Left does not equal right. Right is winning, so I'm going to say Fa minus the force of friction is equal to ma. And then I'm going to look at torque. And I hope you recognize that Fn causes no torque, Fa causes no torque because they're coming off the radial axis. So my net torque is simply the force of friction, okay? And it is causing a torque of I alpha. So how can we solve this question? Well, I know Fg, I know Fn. This one's easy enough to do. So Fg equals, let's see, it's 15 kilogram, 150 newtons, which equals Fn. So that one's easy enough. Okay. But now this guy here is where it gets tricky. These two are the more tricky cases. So the trick is to take this guy and to use it to find A. So I'm a cylindrical hoop. So in a cylindrical hoop, we know our mass is mr squared, and we know alpha is A over R. And I screwed this up. Let me go back. I made the classic mistake. Remember, force of friction, torque is force times radius. Remember, torque is Fr, not just force. So come back here, fix that here as well. Force of friction times radius. So my eventual goal is to figure out maybe what my angular acceleration is, maybe what my force of friction is, maybe the minimum mu required. So alpha is now A over R. So I'm substituting that in. So let's look at FF real quick. Let's see what happens. Well, one R cancels there, a second R cancels there, and FF is just MA. Oh, that was nice. FF is just MA. Well, what can that allow me to do over here? Well, if I know what MA is, let's come right here. This is the trick. If you know what MA is, you can substitute it in. So MA is also just FF. So force applied is twice the force of friction. That's one trick. The other one is I know what my force of friction is because M is 15 and A is 2. So there's my force of friction, 30 newtons. Here's my force applied, 60 newtons. And off we go. Now, I could also do some interesting questions. For instance, I could know the minimum mu required. So our force of friction, because this is static friction, has to be less than or equal to mu Fn. And so the minimum mu required here would be the force of friction is what? Let's see. Force of friction is 30 newtons, less than or equal to some unknown mu times Fn of 150. So mu must be greater than or equal to, what's 30 divided by 150? Let's see, that's 1/5, 0.2. So let's go back over this idea. You draw a free body diagram, step 1. Step 2, draw your net force in the up and left and right, up and down, 1, 2. Third step, write your torque equation. Fourth step, solve your torque equation with A in it instead of alpha. And then start manipulating to see what you're looking for. In this case, I could have asked for the static coefficient of friction minimum. I could have asked for things like my force applied, or I could have asked for things like my force of friction. Notice my force of friction was my force applied was twice as much as you might have predicted. If there was no friction, it would have cost simply 30 newtons. So it would have gone much easier if it had to slide. So let's take a look at example number 2. So in number 2, I've got two masses, M1 and M2. M1 is 3 kilograms. So I'm going to draw that over here. M2 is 2 kilograms. We're spinning over a pulley of mass 10 kilograms. Okay. The pulley turns without the rope sliding or slipping, and maybe models a uniform disk of radius r, 0.1 meters. So the rope does not slip. The system begins at rest. Draw the forces acting on the systems. Solve everything we go. So I'm going to come over here, and I'm going to draw right here on this pulley, right where the rope starts. That's T1. Over here where the rope ends, that's T2. Okay. Then I'm going to come over here and draw my other guys. I've got forces of gravity 1 and 2. So Fg1, Fg2. And of course we know that on this side of the rope that this is also T1 and this is also T2. Now, I know these tensions are not the same because otherwise this disk would not rotate. Okay. So what are my governing equations here? My governing equations, up equals down, so I've got Fg and T1. Now I know the winner is M1, so I'm going to say in that scenario, winning, okay, if you want to consider it that way, I'm going to say Fg1 minus T1 equals Ma. My second one, which is off to the right, is T2 minus Fg2, because T2 is winning this argument, also accelerates at Ma. And I'm going to write M2 here and M1, because that's the only thing moving. And then my third equation, which I can find from my torque equation, is going to say, now who's winning here? Because again, I'm going to put in the winner's protective. T1 is winning, so T1R minus T2R better equal I alpha. So I want to solve for angular acceleration here, and this is going to take me a teeny tiny bit of time. Not a lot, but a little bit. Now, let's talk about what I know from each question. So Fg1 we know is 30 minus T1 equals my M of 3A. That's equation 1 I know. Equation 2 I know is T2 minus 20 equals 2A. And notice I've got 3 equations, 3 unknowns. That's not good enough. So my third equation from torque is going to be T1 times 0.1, so 0.1 T1 minus 0.1 T2 equals I. Now this is a solid guy, so I'm gonna write I over here. I is 1/2 mr squared. So 1/2 of 10 times 0.1 squared, because that's my rule for a solid cylinder. So 10 and 0.1 cancel, but there's another 0.1 so I think that's 0.05. Okay, 0.1 squared is 100th times 1 is 0.1, 0.05. So alpha is 0.05 times, now, I is 0.05. Alpha is A over R, 0.1. Does that make sense so far? So I've got 0.1 T1 plus 0.1 T2 equals, divided by 0.1 is just 1/2 alpha. And I don't know why I wrote alpha, because it's A now. So the question is, from here, can you figure out how to answer this? And the answer is, it shouldn't be too hard. It's a little bit of solving, a little bit of math, but it shouldn't be too bad. First thing I'm going to do is multiply everything by 2 here. So I'm going to get A equals, and if I multiply by 2 here, that's going to be 0.2 and 0.2. So I'm going to write that. So 0.2 T1 plus 0.2 T2 equals A. So I've got 3 equations, 3 unknowns. I should be able to now solve this. It's still going to take a little bit of time, not a ton. I'm going to stick it in over here. So I've got T2 minus 20 equals, twice that again, so it's 0.4 T1 plus 0.4 T2. And then I can do this a couple different ways. I can solve for T2 if I want to. I can solve for T1. It doesn't particularly matter which approach I use. Let's go ahead and solve for, what do I want to do? Solve for T2 doesn't really particularly matter. Let's go over here and solve for T1 actually. I'm going to use this one because this is actually a little bit more straightforward. Do I want to solve for T1 there? That'll give me A. Now I need to come in, let's see. I'm going to let you do it from here. Take your time. Subtract 0.4 T2, right? Solve for T2 or T1 over here. Then plug it in over here. Solve your question. Shouldn't be too hard at this point. These are systems, though. You've got to take it. Once you know one of your 3 variables, you should be able to start unpacking, answer your questions, and do it from there. So give you a few minutes. Try that on your own, maybe 5-10 minutes. I'll post the solutions on Edmodo for you. I'm just not feeling how much you do it. Now, once you know that, once you know alpha, remember, once you know angular acceleration alpha or A, and we're going to do everything in terms of A here. Once you know A, you should be able to use this with rotational kinematics. And as well with E. All right, last one, number 3. So this is called the Great Downhill Race. We'll do a lab today with it as well when you come into class, but let's go and do a real quick example. So I'm given a ramp with a 30-degree angle. Angle's 30 degrees, okay. And the distance is 8 meters, so this distance here is 8 meters. Mass is 2 kilograms, radius is 0.2. 2 meters equals R. Find the following. So let's start with a free body diagram. So first thing, we should know how a hill works by now. Force of gravity straight down. Force normal, perpendicular. And now watch where I draw my force of friction now. Force of friction. That's an important key change to how we were doing it. It's now drawn off the bottom little edge. So what are the equations that govern this scenario? So we should know for the bazillionth time that my net force down the ramp, okay, is mg sine theta, and I'm losing up the ramp, which is force of friction, and that of course equals ma. I also know that mg cosine theta is equal to Fn. And my new one, when it comes to torque, is the force of friction times radius equals I alpha. Now, we are this time, though, ramp with this, did I say it was a hoop or what? Let's see. A ramp is set within a solid ball. So since it's solid and it's a ball, which means a sphere, okay, you'll need to go back to your yellow sheets and look at which one it is. I believe it's 2/5 mr squared. So the I of a sphere is 2/5 mr squared. So we want to solve for the acceleration down the ramp. So I want to find A eventually. So I want to be there. Now I hope you notice I know m, I know g, I know sine theta. So if I can find the force of friction, I can use this equation to answer it. Now, so we go, what about mu Fn? What about mu? And the answer is I can't assume I have maximum coefficient of friction. So I have to go back to that. I might be able to answer an interesting question about it later, which is what part 4 asks. Right now, I'm going to use my torque equation to solve for the force of friction. That'll allow me then to solve for ma. So force of friction times, I'm going to go and find I already wrote it down here. So it's 2/5 my m of 2 and my r of 0.2 squared. So I'm going to have to do, and I don't know what 2/3, it should be 2/5. Hollow sphere is 2/3. So calculate, let's turn this on, 2 divided by 5 times 2 times 0.2 squared. And I get 0.032. So I'm going to plug my stuff in right here. So force of friction times 0.2 equals 0.032 times, now watch what I can do, A over R. I don't even need to use the equation over there. A over what's my R? My R is 0.2, and I can solve for A and the force of friction. So I'm going to have 0.2 times the force of friction equals 0.032 divided by 0.2. So I got 0.16A. So I'm going to solve for the force of friction now, because I'd like to eventually solve for A. So I'm going to say 0.16 divided by 0.2, and I've got 0.8A. So now I'm going to take that and come over here. So M is again how much? Let's make sure I got it right. It's 2. Yep. So 2 times 10 times sine of 30 minus my force of friction of 0.8A equals my m of 2 times an unknown A. So 20, and we hopefully all know what sine of 30 is, which is a half. I'm going to slide this over here, equals 2.8A. So that's 10 equals 2.8A. Divide by 2.8. So I take 10, divide by 2.8, and I get an A of 3.57 meters per second squared. Now, if you take a look at something real quick, if I had just done g sine theta, which is 10 times sine of 30 is 5. Notice I'm rotating much slower. I'm accelerating much slower than I would be if I'm sliding. That's an important difference. When you rotate down a hill, when you roll down a hill, you will not travel as quickly as when you slide down one. What would the minimum coefficient of static friction need to be in order to keep this object from sliding? So we know the force of friction equals, force of friction static. Remember, it is static friction because the fact that it is not moving when it's in contact with ground is mu Fn. So I know my force of friction I can find by right here. It's 0.8 times 3.57. Has to be less than or equal to mu, and Fn is mg cosine theta. So 3 times 0.8, let's see, times 0.8. So that gives me 2.86 newtons is less than or equal to mu, and mg is 2 times 10 times cosine of 30. I'm going to say 2 times 10 times cosine of 30. see what that gives me, 17.3. So 2.86 is less than or equal to mu times 17.3. Divide by 17.3. I'm going to flip mu to in front, so mu must be greater than or equal to 2.86 divided by my answer, and I need a mu of 0.165. So mu would have to be bigger than that in order for this to roll, and that is not a terribly big mu. Most mu's follow under that guise. So what does rolling downhill work like again? Look at your picture. Make sure you can memorize this free body diagram. That's a key difference. It's a key change. So friction is the only thing causing torque. You've got mg cosine theta equals Fn still in the up, in and out. You got down and up still mg sine theta minus the force of friction equals ma. That's still all the same. Please again recognize that when you're rolling down a hill, that your acceleration will be slower. And please remember that the greater the I, the greater the moment of inertia, the smaller the A. The greater the moment of inertia, the smaller the A. And I will show you a real cool shortcut eventually that'll allow you to get to A without having to do any work. And I'll show you that in class. So, so number 5. What is the translational speed of the object when it gets to the ground? Did I finish 4? Let me show you. I got A. It's either 4. What would the minimum coefficient be? Okay, so 5. What is the translational speed of the object when it hits the bottom of the ramp? So we know translational, so I'm going to be in translational world. I'm going to do v squared equals v naught squared plus 2a change in x. Though I really should say change in s because I don't have I'm going along the speed. The final speed is what I'm looking for. My initial speed is 0 plus 2, my acceleration of 3.57, and I travel 8 meters. So I do 3.57 times 8. Take the square root of that guy, and I get v equals 7.56 meters. If you do square root of 2gh, it does not work. If you figure out how far you fell down, it doesn't work that way. How long did it take to hit the ground? So v equals v naught plus at. So my final velocity is 7.56 equals 0 plus 3.57 t. So I'm going to take 7.57 divided by 3.57. It takes me 2.11 seconds to hit the ground. So take a second, try these conceptual challenges, and I'll answer them in a moment. So, is the rolling acceleration down a hill faster or slower than if it slid down the hill? And the answer is the rolling acceleration is overall acceleration is slower than when you slide. Because if you're sliding down the hill, you're not gaining as much momentum of inertia. It's not spinning. All of my energy is going to translational. So that is the simple reason for that. So rolling downhill is slower. Why? Because it's changing some of the energy, it's converting some of the momentum, inertia, whatever you want to call it, into rolling aspects and not just moving it down the hill. If I replace the object with a hollow sphere of the same mass, would the acceleration change? The answer is yes. The inertia of a hollow sphere, the moment of inertia, is much greater than that of a solid sphere, and because of that, my moment of inertia goes up, so my acceleration goes down because it's harder for it to turn. If static friction was not great enough and the object started to slip down the track, would it be going faster or slower at the bottom? The relationship for translational A and angular acceleration alpha is no longer true. Why? The first one is, it's not true because this only is true for the fact that every ounce of turning also turns into translational. So this relationship holds true as long as you do not slide, slip, anything like that. Okay. Now, what would happen to the speed? And this is where it gets a little bit trickier. Realize there's less frictional force when you're sliding, right? Now we're kinetic friction. So if you think of it simply in this, mg sine theta minus force of friction equals ma. It was static friction, now it's kinetic friction, so it makes sense that this number will get smaller, so this number will get larger. So that's the first way you can logically deduce that it'll do that. That's one way of doing it. The other way you think of it is by not rotating, more of the energy is transferred translationally. We'll talk a little bit more about energy transfers in class next block, but you can think of it as energy as well. A tire skidding or slipping is an example when translational is greater than tangential. Can you come up with an example where the angular acceleration is greater? So you ever seen someone that's like in the mud and he starts spinning his tires and he's actually not going very far? That's an example of my angular acceleration. So this statement up here is still false, but most of the time you think of it the other way. You're slipping and sliding, so tangentially is faster than angularly. When you're spinning out, on the other hand, it's the exact opposite. So you have some homework. Got some equations you should still know. And you have 2 practice problems, both of which I give you the solutions to. Number 4 tends to be a little bit tricky. Take your time with it. It is a system question. If you have any questions, you're welcome to come see me about it. But either way, I'll see you on Friday. Talk to you later.